In this video, we're going to establish the idea of cardinalities for sets of infinite size, and we'll use that idea to compare the various sets of numbers that we've seen in the past. Okay, and these sets of numbers are things like the natural numbers, numbers like 1, 2, 3, 4, and so on and so forth, the whole numbers, which include 0 now, the integers, which are both now positive and negative, and so on and so forth. And in this article, we will look at the formal definitions of all of these sets. So if you recall back to chapter 1.1, we defined what cardinality is for sets of finite size, right? And if S is some finite set, we said that the cardinality of S is the number of elements in S. And we said that it didn't really make sense to find the cardinality of a set with infinitely many elements, right? How would we find the number of elements in this set? Well, there's infinitely many. So that really doesn't make sense. So we need to extend our definition of cardinality such that it makes sense for sets of infinite size. And what we will actually do is, instead of comparing the absolute number of elements in a set, we will look at the relative number of relative sizes of sets between infinite sets. Okay, so we say that two sets have the same cardinality if and only if there exists a bijection between the two sets. Okay, so this is how we will sort of establish this notion of cardinality for sets of infinite size. But we also have to make sure that this definition satisfies properties for sets of finite size, right? So let's suppose A is the set A1, A2, and A3. And B is the set B1, B2, and B3. Do they have the same cardinality? Yeah. The size of A is equal to the size of B, both of which are 3. Is there a bijection between the two sets? Yeah. Well, we can just say that the first element in A maps to the first element in B, the second element in A maps to the second element in B, and the third element in A maps to the third element in B. So it's pretty clear that if two sets have only finitely many elements, it is easy to construct a bijection between them. But we will now extend that to sets of infinite size. Okay, so the first set that we look at is the set of natural numbers. Okay, and this is also known as the counting numbers, and these are the numbers 1, 2, 3, 4, and these are probably the first set of numbers you learned about before learning about what the number 0 is. Okay, basically the only thing that's important for us right now regarding the natural numbers is the symbol that we use to represent it is this fancy N. And if you're using LaTeX, it's \mathbbn. Cool. So the next set that we will talk about is the set of whole numbers. Okay? The symbol is very similar to the natural numbers, but it includes the subscript 0. Okay? And the only difference between the set of natural numbers and whole numbers is that the whole numbers include 0. And you can think of, you can remember that by saying, a hole in the ground looks like a 0. Okay? And so we can define it by just listing out the patterns, 0, 1, 2, 3, 4, so on and so forth. But we can also write it as the union of the set containing just 0 and the set of natural numbers. Okay? So these are the whole numbers. And so the question we now need to answer is there a bijection between the set of natural numbers and whole numbers? I.e., do they have the same number of elements? Do they have the same cardinality? Clearly, the whole numbers, have at least one more element, right? Because there's a 0 in the whole numbers, but there's no 0 in the natural numbers. But as we will see, there is indeed a bijection between these two sets, implying that they have the same cardinality. Let's take a look. So first, let's write out the naturals. Okay, we have 1, 2, 3, 4, and so on and so forth. And then let's write out the whole numbers. We have 0, 1, 2, 3, and so on and so forth. And we want some function that will map elements from the naturals to the set of whole numbers. Okay? So what function can do this for us? After a little bit of thought, we realize that everything in the second row is exactly 1 less than the corresponding element in the first row. So our first guess is that our bijection is the function x minus 1. So it takes in some element x from the set of natural numbers, subtracts 1, and spits out the corresponding whole number. So is this a bijection? Well, to check, we would have to make sure that it's both injective and surjective. Okay? Is the function injective? I.e., will it always, given any two different inputs, will the two outputs also be different? Well, yeah, because suppose A and B are two inputs, A minus 1 will never be equal to B minus 1 as long as A is not equal to B. I.e., if f of A is equal to f of B, it means that A has to be equal to B, right? Because if A minus 1 is equal to B minus 1, then A has to be equal to B. So this function is indeed injective. Is it surjective now? I.e., we're asking, will every number in the set of whole numbers have a pre-image? Meaning, will there always be something mapping to every number in the set of whole numbers? And the answer to that is yes, right? We want to know that for all elements in, let's say all elements C in the set of whole numbers, we need to know that there's something mapping to it from the natural numbers, okay? And let's see what we have above here, right? We have that 1 in the natural numbers maps to 0 in the whole numbers, 2 in the naturals maps to 1 in the whole numbers, 3 maps to 2, and so on and so forth. So we see this pattern that f maps C plus 1 from the natural numbers to C in the whole numbers. So that means give me any element C in the set of whole numbers. It could be 10 million if we want. We know that 10 million plus 1 will map to 10 million, right? So any number in the set of whole numbers will always be mapped to by some element in the natural numbers. Namely, it'll be mapped to that number plus 1. Cool. So this extends to another definition that's important to talk about. We say a set S is countably infinite if and only if there exists a bijection between that set S and the natural numbers, right? And if that bijection does not exist, we say that S is uncountably infinite. So that means, since there's a bijection taking us from the natural numbers to the whole numbers, that means both of these are countably infinite. Okay, so now we're starting to talk about this idea of two different sizes of infinity, right? The natural numbers and whole numbers are certainly infinite, right? There's no largest element and they go on forever and ever. But this implies that if a set is uncountably infinite, not only is it infinite, but it has a larger cardinality than the set of elements in the natural numbers and whole numbers, okay? So to show that a set is countably infinite, we need to find a bijection between that set and any other countably infinite set, right? So to show that S is countably infinite, we need to show a bijection from S to the naturals, or to S to the the whole numbers, or to the naturals, or to any other countably infinite set. As we will see, there are quite a few other countably infinite sets that we care about. Okay, and so another way to look at the idea of countably infinite sets is, well, what are the natural numbers? It's 1, 2, 3, 4, and so on and so forth, right? And by finding a bijection to the natural numbers, essentially what we're doing is ordering our set, right? We're trying to find an enumerable order to our set. Okay, so if we find a bijection between our set and the natural numbers, it means there's some way to order it, right? Just as we did for the naturals to the whole numbers. We said the first element, or element 1, is 0, element 2 is 1, element 3 is 2, and so on and so forth. And this property is true because the natural numbers are the numbers we use to count things, right? We use the numbers 1 to denote the first thing we see, 2 to denote the second thing we see, and so on and so forth. So if we find a mapping between our set and the set of natural numbers, it's almost like we're listing out these elements, right? And just as with the natural numbers and the whole numbers, there are infinitely many of both of them, right? But what this process does is that it gives every element some order, okay? It gives every element almost like a weighting number, like at the DMV, but the line is infinitely long. So what finding a bijection between our set and the natural numbers does is it tells you when that number will be counted, or when that number will be accounted for in creating that set, okay? So what we want to do is find some way to order a set. And if we can do that, we say that set is countably infinite. Cool.